Welcome to Online Algebra 2 class. Today we are going to cover section 8-1, inverse variation. So our objective here is to recognize and use inverse variation and to use joint and other types of variation. And our enduring essential understanding is that if a product is constant where the constant is positive, a decrease in the value of one factor must accompany the increase in the value of the other factor. So way back in chapter 2 in this textbook, we talked about something called direct variation. And the formula for a direct variation was y was equal to some sort of constant times x. That means as y went up, x went up. As y went down, x went down, right? And this constant right here could be anything. Could be a number bigger than 1, a fraction, whatever. It made these two relate to each other somehow. So now what we're going to do in this section is, here was my old formula, direct variation. For inverse variation, we are going to have the formula that y is equal to k over x, or that x times y is going to be equal to my constant k, as opposed to for direct variation, the constant k was equal to y divided by x. Kind of like the slope, rise over run. Okay, but for inverse variation, that's a little bit different. So for inverse variation, we are going to multiply the two coordinates to get the constant of variation instead of divide. And my formula, which is y is equal to k over x, can be seen that as y goes up, x can't go up because you're dividing by x. So x has to go down in order to make these two sides equal, right? In order for these two both to always multiply together to be k, if x gets bigger, y has to get smaller, okay? And k means the constant of variation again, okay? So when we look at data, we can identify direct and inverse variations. So direct, we know as one goes up, the other goes up. Inverse, we know as one goes up, the other goes down. And then they have to relate to some sort of constant. So it's possible for it to be nothing. Okay, so let's look at our first problem here. X is going up. So 2, 4, 10, 15. Y is going down. So this could be inverse variation if x times y is equal to my constant. So that means 2 times 15 is 30. Okay. 4 times 7.5 is 30. Good. 10 times 3 is 30 as well, and 15 times 2 is 30. So this is a good representation of inverse variation. My constant is k, so the formula, the function model for the inverse variation would be y is equal to 30 divided by x, right? And so if I plug any x I want in, I would get my y coordinate. So 1 would be 30. 30 would be 1. Right? So no matter what, whatever you plug in for x would give you these numbers on your table. All right, let's try another one. So for this one, let's move this down a little bit. Move this down. As x is going up, y is going down again. Okay, that's good. That means this could be inverse variation. Let's check it out. So in order to be inverse variation, x times y has to be equal to a constant. So that means 2 times 10 is 20. Well, 4 times 8 is not 20. So this is 32. 10 times 3 is not even either one of those. That's 30. And 15 times 1.5 is 22.5. So none of these constants are the same. That means this is neither direct or inverse variation, and so we can't even write a formula. Okay, because this constant, right? These numbers are all different. They're not constant. They're not the same, right? So this particular set of data does not give me something that I can classify as direct or inverse variation. Let's look at the three guided problems. X is going up, Y is going up. So this could be direct. Let's see. So for direct, right, for direct variation, the constant is equal to y divided by x. So let's try it. 8 divided by 0.2 is 40. 20 divided by half is 40, 40, 40. So this is direct variation. And the formula would be that y is equal to 40 times x. Okay? Y is equal to k times x. All right, part B. Part B. X is going up, y is going down. So this could be inverse. We just have to check, right? This could have been direct, but it could have been neither, right? So looking at the data just tells you whether it'll just eliminates one choice, indirect or direct, right? It still could be neither. So we have to check the constant in order to decide whether it's inverse, direct, whether it's one of those two or neither. So for inverse, the constant equals x times y. So that's 0.2 times 40, which is 8. Half times 16, that's 8. 8, 2 times 4, 8. So all of these have a constant of 8. So my equation is y is equal to 8 over x. K divided by x for inverse, k times x for direct. Part C, x is going up, y is going down. So could be inverse. Let's check. I have a feeling here. Half of 40 is 20. 1.2 times 12 is 14.4. So no good. Even though 2 times 10 is 20, 2.5 times 6 is 15. So we have two 20s, a 14.4, and a 15. So this is not inverse. It is neither. Okay. So, and we cannot write a formula like this if it is neither direct or inverse. It's probably still a linear relationship. We could probably do something with that, but we're not sure. All right. So let's determine our inverse variation. Suppose x and y vary inversely, and x equals 4 when y is equal to 12. So they're telling me that it varies inversely, so I know that y is equal to the constant over x, and that x times y is equal to my constant, so 4 times 12 is equal to 48. So my formula is 48 over x. All right, let's graph it. Let's make a table. So what does the graph of this function look like? Y is equal to 48 over x. Let's make a table and see what this looks like. I can't put 0 in there because can't have 0 in the denominator. So we get 1 and 48. Ooh, that's way off this graph. 2 and 24. Almost. 3. 48 divided by 3 is 16. 48 divided by 4 is 12. 5, let's not use 5 because it doesn't go in evenly, but 48 divided by 6 is 8. And then 7, no. And then 8, 6. And we can just keep going with this. 12 and 4, blah, blah, blah. Okay, let's plot this. So 224 kind of off the graph a little bit. Okay. 316 is right there. 1, 2, 3. 4 and 12 right there. 6 and 8. 6, 7, 8. 8 and 6. 12 and 4. Look what's happening here. If I plug in 16, I'm getting it 3. And if I plug in 24, again, a little bit off the graph, I'm going to get 2. So this is not a line, okay? This is clearly not a straight line. So my graph is going to look something like this, a smooth curve, okay? Not a parabola, not a really, kind of looks like part of an exponential function, looks like it's flattening out there. And again, if we plug in really, really, really big numbers, this number is never going to be 0, right? We're just going to get, if we plug in 1,000 for x, we're just going to get a really small fraction, close to 0. This will never, as we plug bigger numbers here, it's never going to go negative. If we plug negative numbers for x, then it will on the left-hand side. But let's just graph this, just this half of this. Could we solve this part? What is y when x is equal to 10? Sure, I have my formula now. 48 over 10, which is going to be 4.8. Okay? And it's on my graph here. Okay, 10, 4.8. Oh, look at that. It's actually pretty close. Let's try a got it problem. Suppose x and y vary inversely. X is 8 when y is negative 7. So my constant is going to be x times y. So the constant is 8 times negative 7, which is negative 56. So my function is y is equal to negative 56 over x. Now what does this function look like? Well, now as you start plugging in positive numbers for x, you're going to get negative answers. So instead of, like my last graph, look kind of like this, it's not going to look like that anymore. Right? We're going to get negative numbers, so it's going to look kind of like that. Right? I don't want to graph this whole thing though. What is it when x is equal to 2? Well, that's pretty easy to figure out. We just plug in 2. And so y is going to be equal to negative 28. Okay. So let's use this to do a model. So your math class has decided to pick up litter each weekend at a local park. Each week there is approximately the same amount of litter. The table shows the number of students who worked at each of the 4 weeks of the project. So that means that we have some variables here. Number of students, time. Time is going to be my independent variable, but it doesn't matter because we're going to figure out our constant to see if this varies inversely. And so it's going to be t times n, the two variables multiplied together. So when I multiply 3 times 85, we get 255. When I multiply times 51, we get 255. 12 times 21, however, gives me 252, and 17 times 15 is 255. So I don't want to go crazy here, but most of these numbers are pretty similar, 3 255s and a 252. So let's just say that this approximately models inverse variation, which is the point. You're not always going to get perfect things when you're trying to model data. So this is kind of close enough. And we can write our equation as 255 over x. If I want to use these two variables, it's going to be the number of students is equal to 255 divided by the time, right? 255 divided by 3. Yeah. No, other way. Sorry. That the time is 255 divided by the number of students. Yeah, that makes more sense. Okay, so the more, right? And as one goes up, the other goes down. As you get more students, then the time it takes to clean up the park goes down. So increasing the number of students decreases the amount of time. How many students should there be to complete the project in at most 30 minutes? So because our function looks like this, k over t, so we have 255 over 30 minutes. So if I look at my data here, I expect it to take less time, right? Or no, sorry, time in minutes. It's gonna be somewhere in here. So 255 divided by 30 is 8.5 students. So you want to finish faster, slower, perfect in there. So we're either going to need 8 or 9 students, depending if I want to finish just over 30 minutes or just under 30 minutes. Okay. Let's try a got a problem. Same idea here. After a storm, your math class volunteers to remove debris from people's yards. Very nice of you. The table shows the time in minutes that it takes for a group of n students to remove the debris from an average size yard. So let's find k. Okay, so here k is going to be 225. 75 times 3 is 225. 5 times 45 is 225. And 14 times 16 is 224. So modeling data, we're close enough. So k is going to equal 225. All right, so the number of students is going to be 225 over the time. And if you want 25 minutes, you're going to need 9 students. Okay. All right, so we've seen many variation formulas in geometry. Some, like the formula for the perimeter of a square, are direct variations. Others, like the volume of a cone, requires 3 or more variables. The volume of a cone, the formula for that, if you're not sure, is the volume is equal to pi r to the third power times h over 3, or all over 3. Or another way to write it is, I've seen it like this, which is 1/3 pi r to the pi r cubed h. All right, so basically volume, there's no variables in the denominator, so this is a direct variation, except there's more than one variable, right? Pi is a constant, 1/3 is a constant. Okay, same formula. It's right down here. Base of the cone would be area of a circle, so that's included in this formula right here, right? But the point is that as the base goes up and the height goes up, the volume goes up, right? This is called a combined variation or a joint variation. So the volume of a cone varies jointly with the area of the base and the height of the cone. So basically what we're looking here is we have some special words when we talk about whether or not we have more than one direct or indirect variation. We say jointly when we have 2 direct variations. So we have jointly and inversely when we have x and y as direct, inverse with w w at the bottom. And direct with x, because there's just one of them. Joint means 2, direct means 1, and inversely with more than 1, right? No special word for that. Okay, so let's try a problem with this where we can use this combined variation. Okay, so the number of bags of grass seed n needed to reseed a yard varies directly with the area, inversely with the weight of the bags of seed. Okay, so basically my formula is going to be some constant because I'm varying directly and inversely, directly with the area, inversely with the weight. Okay. All right, so now I'm going to have to solve for K. And then once I have solved for K, now I answer this question, right? This sentence right here helps me find K. So let's do it. If it takes 2 bags of 3 pounds each, right? N is the number of bags. A is the area to be seeded. Oh, whoops, right there. So this is 3,600. And then over W, the weight. Okay. So now solve for K. So we just take 3,600 divided by 3. And so we have 2 is equal to 1,200 K. Divide out the 1,200. And we have that K is equal to 1 over 600. Okay. So that means that now I can answer this question. How many 3-pound bags will it take to seed 9,000 feet? Probably more than 2. All right, let's find out. Bigger area, right? More bags of lawn seed. So N is equal to, well, K is a fraction, so you could do this, all right? But that's going to make it more complicated, right? We can just set this up as K times A over W. So 1 over 600 times A, which is 9,000, over W, which is 3. Looks a little bit cleaner that way. Okay, so 9,000 divided by 600, and we get that N is equal to 5. So we have 5 bags of seed. And that was a combined variation. Okay, let's finish with applying a combined variation with a word problem. So, gravitational potential energy is a measure of energy. PE, that's my variable. Varies directly, that means we have a constant, with an object's mass and its height. Right? Physicists used G to represent the constant of gravitation, which is gravity. So G, okay, sorry, that's my constant. So we can, instead of write K, we can write G. This skateboarder in the picture has, so my potential energy, a mass of 58 kilograms, potential energy of 2,273 joules. So what we're going to do first is we are going to find the gravitational constant. So we know that potential energy over mass times the height is equal to the force of gravity. So let's plug these numbers in. So we have 2273.6 over 58 times height. Oh, here's the height. Boom, right in the picture. Times 4. So that is the force of gravity. So 2273.6 divided by 58 gives me 9.8. And that might be familiar to some of you. And then most of these, you probably don't really know unless you've taken physics what the unit for joules are. But all these units cancel out, and we get a nice number here. So let's not worry too much about that. Let's just make sure that we understand how to do this problem. And what's the gravitational potential energy? Only we're changing is the weight of the person. So potential energy is going to equal that 9.8 times the new mass, 65, times my height, which is still 4, same half pipe, and we get 9.8 times 65 times 4, which is 2548, and that would be in joules. Okay, so inverse variation, direct variation, joint variation, all sort of just tell you how you are setting up these different formulas to calculate and work with equations. Why do we do this section right now instead of right after direct variation? Is that this leads very well into what we're going to be doing in the next few sections with rational expressions. That's functions over other functions. So some sort of variables in the denominator. Okay? But real quick to finish with these two, going up, going down, could be inverse. Looks like it is. Going up, could be direct. Looks like 80 divided by 16. Yes, this is inverse. This is direct. The formula for here is y is equal to 6 over x. The formula here is y is equal to 5, or v is equal to 5u. And that is 8-1, inverse variation.